Hello, in this video we'll be talking about exponents and logs. So an exponent always has two parts, that's a base and a power. So exponents can be just used to rewrite numbers. So if you have 8, this can be rewritten as 2 power 3. So the base in this exponent would be 2 and the power would be 3. So there's two parts in an exponent. So there's some laws regarding exponents. So the first is that if you have any base to the power of 0, it'll always be equal to 1. So if you have 4 power 0, that'll just be equal to 1. Or if you have 6 power 0, it'll just be equal to 1. So the next law is that if you're multiplying two exponents and they're the same base, you can just add the powers. So if you have 2 power 3 times 2 power 4. So here the bases are the same. So remember 2 and 2 are same. And since you're multiplying, you can add these two numbers. So by adding that, you'd get 2 power 7. So you keep the base the same and just add 4 and 3. So if you had 3 power 2 times 3 power 6, since bases are the same and you're multiplying, you can add 2 and 6 and keep the base the same. So that'd be 3 power 8. So similarly, if you're dividing two numbers and the bases are the same, if you're dividing two exponents, and the bases are the same, you can just subtract the powers. So if you had 4 power 6 divided by 4 power 2, since the bases are the same and you're dividing, you just subtract 6 and 2 and keep the base the same. So 4 power 4. So you had 12 power 9 divided by 12 power 6. Since bases are the same and you're dividing, you just subtract 9 and 6, which will give you 12 power 3. And you keep the base the same. So here, if you have an exponent, and this is to the whole power of some number, maybe 4, for example, you would just multiply these two numbers. So this could be written as 2 power 12. So what I've done is just multiply 3 and 4. So if you have 6 power 2 to the whole power of 7, you just multiply these two numbers. So that'll give you 6 power 14. So this law can also be used to rewrite exponents. So if you have 7 power 14, this could be rewritten as 7 power to the whole power of 7. Because you just multiply 7 and 2, which would also be equal to 7 power 14. So the next set of laws is that if you have a base to the power of a negative power, you would get so if you had 2 power minus 3, it becomes 1 over 2 power 3. So if you had 4 power minus 6, that would be 1 over 4 power 6. Yeah. Next is that if you have a base to the power of a fraction, it would result in this. So if you had 2 power 4 by 6, so base to the power of fraction, it result in 2 power 4 root 6. So this is because here m in this case is 4 and n in this case is 6. So here, according to the law, m goes here and 6 is the power of a root. So here what I've done, so 4 goes here and 6 is the power of the root. So another example would be maybe 3 power 1 by 2. So this could be written as 3 power 1 divided, the root of 2, which would just be equal to root 3. So the last law we have is that if you have an equation where on either side your bases are the same. So on either side you have 2 power x plus 3. So on one side you have 2 power x plus 3, and the other side you have 2 power 2x plus 4. So since your bases are the same on either side of the equation, you can equate the powers. And using that, you can solve for x algebraically. So x plus 3 would be equal to 2x plus 4. And now you could just solve this equation algebraically. So you'd get 2x minus x is equal to minus 1. Yeah. So now we could work on a question. So for part A, it says 2 power m is equal to 8 and 2 power n is equal to 16. So with the law that a power m is equal to a power n, we can solve part A. So 2 power m, so notice that 8 and 16 can be both rewritten as powers of 2. So 8 can be written as 2 power 3 and 16 can be written as 2 power 4. So 2 power m is equal to 2 power 3, and for this 2 power n is equal to 2 power 4. So since on either side of the equation the bases are the same, we can equate the powers. So m is equal to 3 and n is equal to 4. So now we can move on to part B. So we'll have to solve the equation 8, 2 power x plus 1 is equal to 16, 2 power x minus 3. So in this equation, we can notice that both 8 and 16 can be written as powers of 2. So using part A, so we can rewrite 8 as 2 power 3 is equal to 8, and 16 can be written as 2 power 4. So 2 power 3, 2x plus 1. So I've just rewritten this equation using this as the base. And now we can do the same for this equation. So for this exponent, sorry. So you can write 2 power 4, 2 power x minus 3, 2x minus 3, and then now we can simplify. So using the previous law that a power m n is equal to a power mn, we can simplify this. So this would be 2 power 6x plus 3, because remember it's 3, 2x plus 1. So this will be multiplied with each and every term here. So 2 power 6x plus 3 is equal to 2, 8x minus 3. So what I've done is 4, 2x minus 3. And that would be simplified into 8x minus 12, sorry. Now, since on either side of the equation, the bases are the same, we can just equate the powers. So 6x plus 3 is equal to 8x minus 12. So that become 15 is equal to 2x, and x is equal to 15 by 2, or 7.5. Yeah.
Hey everyone, so now we'll be looking at the rules that logarithms, or logs, follow. So the first rule includes whatever the base is, any integer, if the argument inside is 1, then the result will always be 0. So log base 10 of 1 is 0, log base 5 of 1 is 0, you get the idea. The second rule is, if the base and the argument are both the same number, then the result is always 1. So log 2 of 2 is equal to 1, log 10 of 10 is equal to 1. So now when we're adding logs with the same base, that's very important. They have to have the same base, then only can we add them. So say it was log base 10 argument of 2 and log base 10 argument of 3. Then the result will be log base 10, the base remains the same throughout, but then the argument inside is the multiplication of the two arguments here. So if it was 2 and 5, then it would be log base 10, 10, because 2 times 5 is 10. And you know, if the base and the argument is same, it becomes 1. So in that scenario, it'll be 1. But this is the general rule you follow when you add logs with the same base. And now when we look at logs with the same base, but now we're subtracting them, in the result, you divide the arguments to get the final argument. So say it's log base of 10, 2, and minus log base 10, 1, then that means the resultant would be log base 10, 2 over 1, which is just 2. So now the fifth rule is, so any log with the base of e, which is a number on its own, so whatever the argument is inside, it'll turn into a natural log, which is ln. So log e of 5 is ln of 5. Log e of 7 is ln 7. So this natural log is a separate identity of its own, and it follows all the rules we've mentioned here. So the sixth rule, so when you have a log where the argument is to the power of something, in this case n, you're able to switch that power and bring it to the front. So it becomes n into log m. And then you can bring it back too. So n log m can be rewritten as log m, and the argument is to the power of n. So this is a very useful trick that they will test you a lot on. So this is a pretty key rule. The seventh rule is one that involves switching the bases. So say you have a singular log with a base of b and an argument of a. You can then rewrite that as log a over log b. But then the base is the question, like what would you put the base as? So in this rule, we learned that we can put the base as anything, as long as they match on both this side and this side. So say I want as the base as c, and then here also I want it as c. This is the same as this. You can basically rewrite a singular log by splitting the argument and the base into two separate logs, like this, and then you put the base in each individual log as any integer you want. This is still equal to this. This may be useful in canceling out terms. For example, if I were to change the base, in this case to b, we know that this is equal to 1. And this just brings you back here. So this is pretty straightforward in this scenario, but then in terms where you don't know what this value is, it may be useful in canceling out terms in questions. And so the last rule, so when you have a base to the power of a log, and the base is equal to the base of the log, that means you can cancel it and you just get x, which is the integer or the argument in the log. This is not tested as much, but it's still a pretty unique rule to remember. So now I'll be solving two sums. Both will test the rules that we just went over. So the first one is a simplification sum. We have this large logarithm, like a series of logarithms, and they want us to express this as a single log in its simplest form. Okay, so how I would approach this is, so firstly, we all know that they all have the same base, because ln is just the same as log e. And since they're all ln, they all have the log e, and thus the base is the same. So this means we're allowed to use the rules for subtraction and addition. So let's start. So ln, we have to write it as one single logarithm, right? So you have x squared minus 1, that's the first one, and this is minus 2 ln x plus 1. If you guys remember, we can bring the 2 here as a power. So if we were to rewrite this as ln x plus 1 squared, So we can see that this is subtracting this. So that means this argument will be over, like when you divide, it'll be over this. So the final thing will be x squared minus 1 over x plus 1 whole squared. And now we have a plus x squared plus x. So that's multiplication. So we can just write it on the top because we're multiplying. So this is the logarithm that we have now. And they expect us to simplify it to its simplest form. So we have to cancel out whatever is inside and make it simplified. So first off, there is a rule. It says a squared minus b squared is the same as a plus b, a minus b. So if we look at this log, we can see that x squared minus 1 follows this. So if a is x and b is the square root of 1, which is just 1, we have x squared minus 1 becomes x plus 1 and x minus 1. So we then rewrite this thing as x plus 1, x minus 1, x squared plus x over x plus 1 whole squared. Actually, before I rewrite this, we'll now also try and simplify x squared plus x. So we see at the bottom, we have x plus 1 whole squared. We have an x plus 1 here from simplifying, we have an x plus 1 there from simplifying the x squared minus 1. So what we can do is, we can remove that and remove that. So that gives us only an x plus 1 at the bottom because it's squared, right? And we've only removed 1 of the factors. So to remove this x plus 1, I can then rewrite this as x plus 1 into something. So then logically, it would be x plus 1 into x, because this x plus 1 into x would give me this. So again, if I were to remove this and this, that would leave me with ln x minus 1 x over 1, which is the same thing. And we have x here because of that, and we have the x minus 1 from here. So the final one would be x squared minus x, because the x has been multiplied into both. This should be the answer for this. Okay, so now we look at the second sum, and it's the answer that they want should be in the form of x is equal to dot dot dot. We're expressing the answer in that form. So what I identify as soon as I look at this is that the arguments for each natural log are all multiples of 2. So there's a way to bring them all to a 2 to the power of something something. So that'll allow us to simplify the overall expression. So that's what I'm going to do. See, so on the left side, we already have ln 2 4x minus 1 is equal to, so 8 is equal to 2 to the power of 3. So if I were to rewrite 8x plus 5 into 2 to the power of something, that would mean 3 to the power of x plus 5. Because we're changing that 8 into a 2 to the power of 3. And yeah, it's straightforward from there. So we have to carry in the 3 inside, so that will become 2 to the power of 3x plus 15. So then here we get, here we get ln 2 3x plus 15 plus, so here it's not a natural log, it's a normal log. So I'm going to still try and get the base and the argument to be 2, because when the base and the argument is the same, we can cancel it and get only the argument as the final value, which simplifies it immensely. So log 2, so if you do the same thing, 16 is 2 to the power of 4, so 16 to the power of 1 minus 2x same as 2 to the power of 4 into 1 minus 2x, is equal to 2 to the power of 4 minus 8x. So it becomes 4. We get 2 to the power of 4 minus 8x. As I said, this can get cancelled. So we get ln 2 4x minus 1. And I would want to bring this ln to the other side, because, you know, bringing the natural logs on one side is better. So we get that because it becomes minus because we've carried it over the equal sign, is equal to, since we've cancelled that, 4 minus 8x. And now this is referring to the rule of, you know, normal subtraction, because the base is the same, as ln is the same as log e and log e. We can subtract them normally, as we would. So we get ln 2 to the power of 4x minus 1 over, well, I forgot on 2 there, 2 to the power of 3x plus 15. And this is equal to 4 minus 8x. So when we have powers dividing like this, you should know by now that we can just subtract them. So when we simplify that, we get, so 4x minus 3x is x, minus 1 minus 15 is minus 16. This is equal to 4 minus 8x. So now to isolate this x, I'm going to bring it over, because, you know, it's a power, I can do that. So I get x minus 16 into ln 2 is equal to 4 minus 8x. But still, the x is not isolated from this side. So I multiply it to get x ln 2 minus 16 ln 2. You know, I've just multiplied each one. Is equal to 4 minus 8x. So then if I want to bring all the x terms to one side, I get x ln 2 plus 8x is equal to 4 plus 16 ln 2. So now if we look at that over here, and we take the x out common from the left side, we get x ln 2 plus 8 is equal to 4 plus 16 ln 2. And now if we divide this side by this, we get x is equal to 4 plus 16 ln 2 over ln 2 plus 8. So that's it. This was, I would say this is around a 4-mark question, because just to show that. And we have done that. We have showed the answer to this whole thing in terms of ln 2, because we only have ln 2, and it's in the form of x is equal to. So that's done.